Okay, so what I'll first do is take up the geometrical interpretation once again and try to again distinguish between what we were trying to do in the numerical integration versus what we are trying to do in the ODE solving. The specific problem that we are going to solve in the ODE solving techniques is dy by dt equal to f of y comma t with y given at time t0 equal to y0. Okay. So what we are interested in doing in case of ODE solving is we want to find out the value y as a function of t starting with some value of y0 given at time t0. Okay. So we start with this particular value y0 and then try to get the overall curve y of t as a function of t, and this is, let's say that if we have an analytical solution for this particular problem, let's say that analytical solution, that means looks like this particular curve. Okay. So what we are going to do is the function f of y comma t at time t0 and at the value of y0 is going to be nothing but this particular slope that we have. This slope is going to be f of y0 comma t0. Okay. So what we are going to do in an ODE solving is use this particular value of slope in order to predict or in order to move on to the next point, which is going to be y1 comma t1. Now this particular next point can either lie exactly on the actual curve, but usually there are errors that are associated with any numerical technique. Okay. So what is going to happen is that the next point is not going to be the white point that I have shown. I am going to use white curves in order to show the actual curves, and I am going to use yellow dots in order to show the numerical solution. So what will happen in the ODE solver, based on the ODE solver, is we will reach the point which is shown by the yellow x over here. Okay. So over here then the function value f of y1 comma t1 is going to then represent the slope of the numerically computed curve. Okay. And based on the slope that we compute over here from time t1, we will then move on to time t2, and the slope might be like this, and then we might end up at this particular yellow point. Okay. And we will keep continuing this over and over again, and perhaps finally the curve that we will get essentially is, perhaps for argument's sake, looks something like this. So this is the numerical solution and this is the actual solution to the problem. So what we are interested in doing when we try to solve an ODE problem is we are interested in getting the curve y as a function of t. Okay. Now when we are actually solving the integration problem, we are not interested in getting this curve y as a function of t, but instead what we are actually plotting is we are plotting the function f of t against t. Okay. So what this function f of t represents is nothing but the slope of this particular curve at various points, and let us say that particular curve, the slope f of t represents something like this. Okay. In that case, the integral from a to b, or integral from y0 to integral from t0 to t1, or rather than saying t1, let me call it tn, that integral is going to be the area under this particular curve. Okay. Now the first difference that we find is that for the ODE solver we have this function f, which can be a function of both y and t. In case of an integration, it is going to be just a function of t. Okay. That is going to be one difference. The second difference is that it's the integral is an area under the curve, whereas in solving the ODE we are actually trying to trace the curve y of t rather than looking at the curve f of t. Okay. That is the other difference between ODE and integration. The third difference is that because this function dy by dt is in general going to be a function of both y and t, the ODE solving method is going to be a more general way of solving these problems rather than an integration method. Okay, that is going to be a third difference between this. Now let us look at the PFR problem. Now what we physically mean by the plug flow reactor problem is, let us consider that we have a tube of this sort. Okay, let A be the area of tube. At the inlet what we have is, we have the system flowing in, we have a solution of any particular compound, let us call that compound A, and the reaction, let us say we have the reaction going from A to B, okay, and ACS let us say is the area of cross section of the tube, okay. So the volume is going to be nothing but ACS multiplied by X, where X is any distance from the inlet, okay. So what happens is that the species A keeps getting converted to species B because of any reaction that takes place within this particular system, and the overall equation for this system can be represented in the form of dx by dV equal to the rate of reaction R, which is as given as a function of x divided by f, okay. So this is what we get as dx by dV, okay. So now in the ODE solver what we are going to do is, we are going to find the conversion So we are going to find a conversion as a function of the volume of the PFR. Okay. If some of you who have covered or who have already gone through reaction engineering courses will perhaps recognize what I mean by this. If you have not gone through a reaction engineering course, basically I will just give you an overview of what happens. As the species A enters into the reactor, into the plug flow reactor, it gets converted because of the reaction to the species B, and this particular equation represents how the species A, or how quickly this particular species A is going to get converted within the reactor. So X represents conversion, that means how much percentage of species A has been converted to species B, okay. So what we get if we are going to plot conversion against volume, okay, initially when the concentration of A is high, that means closer to the inlet where the concentration of the species A is high, the rate of reaction is faster, so A gets converted very quickly. As we move towards the end of the reactor, so at the inlet the volume of the reactor is 0, okay, we are starting right at this. As we keep going towards the right, the volume keeps increasing, okay, that is what is happening, that is what this represents. Now as the volume increases, okay, the amount of A that is converted increases. The rate of conversion of A is going to be very fast right in the beginning, that is because there is a lot of A that is available for reactions to take place. As we go towards the other end of the reactor, as the amount of A depletes, the rate of reaction reduces. As a result of this, the conversion curve that we are going to get as a function of volume is perhaps going to look somewhat like this. The rate of reaction is high in the beginning and then it starts to taper off. Maximum conversion is going to be 100%, the conversion cannot exceed 100% at any given time, okay. So in an ODE solving, for a plug flow reactor, the question that we are trying to ask is, how does the conversion of A change as we increase the volume of the reactor. Okay, so this is the question that an ODE solver, or while ODE solving, we are trying to ask. Okay, now the same equation we will rewrite it in a different form. What we will do is we will take dV on this side, and F by R will take on to the left hand side, and we will write this in the form dx divided by R of x multiplied by F. I actually missed FA0 over here to keep it consistent with the notation that we have used in the previous lecture. FA0 multiplied by dx divided by R of x is going to be equal to dV. Okay. Now if we are going to plot the 1 by R as a function of x, in that case the volume that is required to meet a certain conversion is going to be the area under the curve. Okay, so what we are plotting is FA0 divided by Rx. Let's not worry about the negative signs over here, as a function of x. Okay, so what we plot is how the value FA0 divided by Rx changes as the conversion changes, and let's say that particular value changes like this. Okay, so now the question is, what is the volume of the PFR that is required in order to meet a certain conversion? In the previous module, what we said is we wanted to get 90% conversion. Okay, that means x equal to 0.9. So what is the volume that gives you 90% conversion? Okay, so the volume that gave us 90% conversion was the area under the curve. Okay, so integration for solving design equation okay. So in this case OD is for solving the PFR equation, integration is also can be used for solving the design equation of the PFR, but the question that we are going to ask is going to put in a slightly different context, and the question that we are going to ask in case of solving the design equation is what volume of PFR is required to achieve a specific conversion value. Okay, so we have now recast the same question in a slightly different way, and in that we are asking what is the volume of PFR that is required to achieve a certain conversion. Now the question is, how can we use an ODE solver in order to answer the same question? The way we can use the ODE solver in order to answer the same question is, let us look at the point at which conversion is 90%. So the point at which conversion is 90%, and draw the horizontal line over here. The value of the volume that you get over here is the volume of PFR that gives you 90% conversion. Okay,